Hi folks, in this video we talk about using interpretations in first order logic. For example, you can use interpretations to prove that arguments are invalid or prove that sentences are possibly false. For example, stop your videos now and see if you can give me an interpretation that shows that this argument on the screen is not valid. Okay, in order to do that, your interpretation has to make the premises true and the conclusion false. That's what would make it a counterexample. Now, interpretations in first order logic are more complicated than in propositional logic because we need to not just assign truth and false values to the atomic sentences and determine which row of the truth table we're on. We need to actually tell you what these predicates mean and what the domain of quantification is. So there's really three separate parts of a first order interpretation. For example, P and Q are the predicates in this sentence, so I need to tell you what each of those things means. I also need to tell you the facts so that we actually know whether these premises and conclusion are true and false. And lastly, there must be a domain of quantification in order for these quantifiers to have truth values, for example, for us to know whether everything has property P. Sometimes the domain is implicitly understood, but I'll make it explicit just so we're entirely clear. There's many different interpretations that could do the trick. So yours doesn't have to look exactly like mine is, but there should be certain structural properties, certain structural aspects that are going to be the same. For example, I decided to let P be being a dog and Q be happy. And no matter what, whatever you made your property Q, you have to make sure every object in your domain has property Q because premise 2 has to be true. So that's why, I'm talking about Rufus and socks in my facts. Those are the things in my domain. So I made both of them happy just so that premise 2 comes out true. I also made sure to make not everything a dog. That's why socks is a cat, so that my conclusion is false. And lastly, since Rufus is happy, it's true that all the dogs are happy. So premise 1 is true as well. So this interpretation is the counterexample. Now, technically speaking, if we wanted to make an informal proof here, we could spell out in English exactly why this counts as a counterexample. So I did that here just to make it abundantly clear that this interpretation shows that the premises could be true, and while the conclusion is false, thus the argument is not valid. Now, counterexamples are not the only things you can do with interpretations in first order logic. For example, you can show that sentences are not first order validities. If this sentence is possibly false in first order logic, then it's not a validity. See if you can give me an interpretation that does that, that shows that the sentence is not necessarily true. So pause your videos now and see if you can fill in the rest of this interpretation. Okay, that was your chance to pause the videos. Notice there's a new part here, Stan. Because there's a name in these sentences, the meanings, you have to tell me who that means. Who's the referent of Stan, or the denotation, what the name Stan refers to. So this interpretation is slightly more complicated than the previous one, but it really has the same structural parts. Okay, now it turns out you can sometimes use the obvious interpretation. I just let likes mean likes, and threw a ball to means X threw a ball to Y. And I just let Stan mean Stan. So you don't necessarily have to be incredibly creative in your interpretations. If letting these predicates stand for their intended meaning works, then you can just go with it. So that's what I did here. Now I need to make sure somebody likes Stan. That you could use Stan himself perhaps, but I decided to add another person into my domain. So I had Tamar like Stan, and that's why this antecedent is true. My domain, I just said I only have two people, Stan and Tamar. Now, I've specified some facts that we know the truth value of this, but my interpretation is not yet complete. So I need to know some more facts in order to really know this sentence could be false. If your interpretation is somewhat like mine, then you have something else here. So what I need you to do is specify what else goes there. Pause your videos and see if you can tell me what additional information for my interpretation I would need to add into this red question mark in order to really know that the sentence might be false. Okay, that was your chance to pause your videos. I'm going to give you some choices. If you have no idea what's going on, here's a couple of choices to choose between. One of these facts is the additional facts we need to go over here, so we really know what's happening. See if you can figure out which of those is the right answer if you couldn't come up with it previously. All right, the right answer is both. We need to know that they both threw a ball to Stan. That's the only answer that works. Now, why is that? This is somewhat tricky, so what I'm going to do, I'm going to move some of the other information off the screen. Let's talk exactly why this interpretation makes this sentence false. The main connective is this arrow, so I need to make this arrow false. The only way to make an arrow false is to make the antecedent true and the consequent false. Now, I made tomorrow like stand, so my antecedent is true. The consequent is this negation right here. I need to make that negate. That's the wide scope connective in my consequent. Now, how do I make a negation false? I need to make the thing inside its scope true. That's why I need to make it the case that everybody threw a ball to Stan. Remember, Stan is in the domain too, so that means Stan has to throw a ball to Stan. He has to throw a ball to himself. You know, like throw the ball up in the air and catch it in order for this to be true for all objects in the domain. So if this is true, then my negation is false. If my antecedent is true and my consequent is false, then the arrow is false. So that's why this is the interpretation that actually works. Okay, that might have been sort of a tricky example. So let me give you one more to practice on if you didn't get it. Here's a new sentence. Something is smaller than A, therefore it's not true that everything is larger than A. Pause your videos and give me an interpretation on which this thing is possibly false. Okay, that was your chance to pause your videos. Your interpretation, structurally speaking, needs to look something like this. I need to assign meaning to the smaller predicate, the smaller than relation. I need to assign a meaning to larger XY relation. I need to assign an object to A in a domain and some facts, etc. So how did you fill in this table? Well, here's the answer I went for. I used the same interpretation as with the previous argument, because structurally this is identical to the throwing the ball sentence. So your interpretation before would work perfectly. Remember, logic is all about structure. That's all that matters. What I'm wondering is did you notice that you could not use smaller and larger than? So don't be fooled and always assume that the smaller than predicate has to always be interpreted as smaller than. Remember, first order logic only knows the meaning of one predicate, identity. Every other predicate might have an intended interpretation, but that doesn't mean it is forced on us. And when you're trying to give first order counterexamples or show in a sentence is not a first order validity, you might need to interpret it in a counterintuitive way. So, for example, what if you did use X smaller than to mean smaller than? If you did that, your answer did not work. There's a structural problem, because what if something is smaller than A? Well, then this sentence says it's not true that everything is larger than A. Well, if something is smaller than A, then it's not true that everything is larger than A. Then this thing is true. So if you use these predicates in their intended interpretation, this sentence is necessarily true. This actually counts as a logical truth, basically, if these are given their intended meanings. Only if they're given different meanings could this come out as possibly false. So this is a logical truth, but it's not a first order validity. So there's 2 points here. One is, don't be fooled by intended interpretations and assume that you always have to interpret the meanings of these things the way in which the predicates are intended to be. Secondly, if an interpretation works for one sentence and another sentence is structurally identical to it, then the interpretation will work for it too, because logic is all about structure. Okay, thanks.